So now we're going to move on to the second measure of correlation, which is Spearman's rank correlation coefficient. So this is similar to PMCC in the fact that it measures correlation, but we usually use it when the range of data is different, so correlation isn't as obvious. So Spearman's rank correlation coefficient is used when two measures are of different scales, judged in different ways. One or both of the piece of data are non-numerical. And also to this, if one of the sets of data, if one or both sets of data are already ranked. So those are the four reasons why we'd use Spearman's rank correlation coefficient over PMCC. Now, in an exam, usually it will tell you which one to use. If it doesn't, then you have to think about these four factors. If it tells you to use a certain one, make sure you use the one that it tells you to use. These two tests are paired together, which means that if in the question it specifically says that you cannot use PMCC, that is a massive hint that you should be using SRCC. And we perform the hypothesis test in the same way. Again, it's split into one-tail and two-tail tests. Again, same as PMCC, we have to use the formula booklet to find the critical value. However, this time it's on page 24. You need to be careful when you're doing PMCC and SRCC that you read the top of the page, making sure that for SRCC it says critical values of Spearman's rank correlation coefficient. Because the tables do look very similar, you need to be very careful with that. Now this time, when we're writing our null hypothesis, instead of rho, we're going to be using RS. And for our alternate hypothesis, our H1, we're going to be using RS is greater than or less than 0. And the reason for that is that rho represents the population correlation coefficient and R represents a sample correlation coefficient. So throughout this we are going to be using RS, which is a rank correlation coefficient. So we need to be careful between the difference of those three symbols. You can see again that I've done a snippet from the formula booklet to show the table. And you can see again it's got on the top one-tailed and two-tailed. For this first bit, because we're only looking at one-tailed tests, we're going to be reading across the top again. And again down the side it's got the sets of data. So the first example, we're seeing if there's a link between population and area. Here we're specifically told that we are looking for a positive correlation. So as I said before, our H0 is going to be RS equals 0, and our H1, in the same way as it was for PMCC, if we're looking for a positive correlation, we want that to be greater than 0. If we're looking for a negative correlation, we'd want that to be less than 0. Now, as it says here, we need to rank the populations and areas separately. And that's very important because in some of the hypothesis tests that we do, we will rank the set of data as a whole set. But this time we are ranking each of these separately. So to begin with, we'll rank the populations. And we're going to start smallest to biggest. The reason why I like to do everything smallest to biggest is that some hypothesis tests that we come across later on require you to do it smallest to biggest, otherwise it doesn't work. So if we practice that now, we get used to the fact that we should be trying to use smallest to biggest where possible. So if we have a look here, Liechtenstein has the smallest population, so that's going to get the rank 1. The second smallest population is Iceland, which gets the rank 2. Then Malta, which gets the rank 3. Then Sweden, which gets the rank 4. UK gets the rank 5. France gets the rank 6. Pakistan gets the rank 7. USA gets the rank 8. India is 9. And China is 10. Then we need to rank the areas, again, smallest to biggest. If you did have to do biggest to smallest, then you would rank everything biggest to smallest. So just bear that in mind, that you need to rank these two sets of data in the same way. So again, Liechtenstein has the smallest area, but this time Malta has the second smallest area, followed by Iceland, and then the UK, then Sweden, then France, then Pakistan, then India, then China, and then the USA. Now, when we put these values into our calculator, we are now only going to be entering the rank. So we're only going to enter these numbers here and these numbers here. We're going to now ignore the data from now on. And as it says here, we do it in the same way as we do PMCC, but we're doing it with the ranks. So, typing those into our calculator, we have 5, 8, 10, 7, 9, 3, 6, 1, 4, 2, and 4, 10, 9, 7, 8, 2, 6, 1, 5, 3. And as always, just quickly double check that you've entered them all incorrectly. Then we're going to calc, reg, x, a plus bx. It's still in the calculator written as r. However, this time when we write it down, we're going to write rs, as I explained before. So that gives us 0.939. Same as we did with PMCC, that's our test statistic. Then we can use the critical value table. There are 10 different countries that we're looking at. It is a 5% significance level, and it's one-tailed because we're looking at positive. So one-tailed, 5%, 10 pieces of data gives us 0.5636. So our critical value is 0.5636. And we're making the same comparison as we did with PMCC. Here, our correlation between the ranks is stronger than we needed it to be from the critical value table, so we're going to reject H0. So as our test statistic is bigger than the critical value, we're going to reject H0 at a 5% significance level. There is sufficient evidence to suggest a positive correlation between, and we need to be careful here because when we had a look at our correlation, we didn't actually look at a correlation between the population and the area. We had a look if there was a correlation between the ranks. So we have to make that clear in our conclusion. So it's going to be between the ranks of population and the ranks of area of countries. So this first example had both of them still being numerical numbers in the data when we started. However, as I explained before, sometimes the data won't be like that. So we have a second example here. We have a company which is replacing a fleet of cars. 8 of the models are considered, And the transport manager ranks them from 1 to 8 in order of performance. A saleswoman is asked to use each type of car for a week and grade them to their suitability for the job, where A is suitable and E is unsuitable. And you can see here that she's also used a plus minus at system with that. And then we're investigating at a 5% significance level whether there is a positive correlation between the transport manager's ranking and the saleswoman's ranking. Well, you can see here from the data from the transport manager, they have done this where one has gone to the highest ranking one. Because if we compare these two, we would be expecting some kind of correlation between the two because of the questions that were being asked. And usually we do rank one as being the best, even though it's the smallest number. Which means that when I'm ranking, I can either re-rank my sales manager's rankings so that they're smallest to biggest, or I can just rank my saleswoman's grades so that they are going from smallest to biggest. So we'd start off with the D minus first. Because I like to keep it so that we're always ranking smallest to biggest, I am going to reverse the ranking of the transport manager's rankings. However, as I said, you could have just ranked the saleswoman's grades the opposite direction to what I'm going to do. So, 8 is the smallest rank, so that's going to get a 1 now. 7 is the next, then 6, then 5, then 4, then 3, then 2, and then 1. On this side here, the lowest grade, A, B, C, D, so we're looking at the Ds. D minus is lower than D, so that's going to get the 1, and then the D is going to get the 2. Then looking at the Cs, we've got a C and a C plus, so the C is going to be lower than the C plus, so that's going to be 3, and that's going to be 4. And then we have a situation here. We've got B, which is going to be 5. But then we have 2 B pluses. So we have 2 things here that have the same value. And because they have the same value, they need to get the same rank. Because they need to get the same rank, we need to think about what ranks they would get. I've already got 1, 2, 3, 4, 5. So the next 2 would be 6 and 7. And because I need to split that rank between 2 numbers, I then need to divide that by 2. Which means that if I had 3 things the same, I would add the 3 ranks that they would get together and then divide by 3 instead. So just be careful when handling any of the tied rankings. So this gives me 6.5, which means that both of the B pluses will get a rank of 6.5. Now it's a good idea to write this at the side because it reminds you which ranks have gone. So 5 is there, then 6 has gone and 7 has gone, which means that the last one left for the A minus is going to be 8. So now we are going to type these into our calculator. So we have, well, remember that we're typing in the blues. When we put them in, I'm just going to delete my data. And remember that we are looking for a positive correlation, which means that my H0 is going to be RS equals 0, and my H1, because it's positive, is going to be greater than 0. Typing these values into my calculator, 4, 8, 2, 7, 1, 3, 5, 6, and then 5, 6.5, 1, 3, 6.5, 2, 4, 8. Double check that what we have here is correct. And then we're going into A plus BX again. And we end up with an RS value of 0.323. Remember that that is our test statistic. Looking up our critical value, we have 1, 2, 3, 4, 5, 6, 7, 8 different models of car. It's 5% significance level and it's one-tailed, which gives us 0.6429. And again, looking at this, making the comparison between the two, this time our test statistic is smaller. So as the test statistic is smaller than the critical value, we would accept H0. This time we don't have a strong enough correlation to say that we found something. At a 5% significance level, there is insufficient evidence to suggest a positive correlation between the transport managers ranking and saleswoman's ranking. Now, if you had decided to keep these ranks this way round, then you would have had to rank these biggest to smallest, which would give us 1 for the A minus. Then B plus, the two B pluses would come next, which would be 2 plus 3 divided by 2, which gives us 2.5. So that'd give us 2.5 and 2.5. 3 for the B, 4 for the B plus, C plus, sorry, 5 for the C, 6 for the D. Oops, sorry, I forgot to double check my bit next to it. Let's start that again. 1, then as we did here, 2.5 and 2.5 for the two B pluses. And like I said, double checking which ranks have gone. 1, 2, 3 have gone. So B gets 4, C plus gets 5, C gets 6, D gets 7, D minus gets 8. And then you would be typing into your calculator the green ranks and the transport manager's ranks. Now, if you failed to notice that the transport manager's ranks had gone from the best to the worst, so you ranked these numbers the wrong way around, then what you would have found is that your RS value, your test statistic, would come out to be negative. The issue with that is that it says here that we are looking for a positive correlation. So that's always a good way with one-tail test that you can check that you have ranked both sets of data correctly, is the direction, the sign that you have, suggesting what you have been asked in the question. In this case, positive correlation means we're expecting to get a positive number here. Another important thing to note is that if we end up with a negative RS value at any time, same as what we did before, we'd write that down as our test statistic and then we'd be looking at the modulus of that to do our comparison. I'd now like you to pause the video and give the Now You try a go. So hopefully you paused the video and gave the Now You try a go. As you can see, again, we end up with some tied ranking in the distance. They would get 5 and 6, so we divided that by 2 and got 5.5 for each. Remembering, ranking them smallest to biggest each side. Our H0 would be RS equals 0. Our H1, because it says here we're looking at a negative correlation, will be RS is less than 0. And when we put that in our calculator, we get minus 0.850, which is our test statistic. And as I was just saying, as we did with PMCC, we would have a look at the modulus of that, the size of that, and so our size of the test statistic is 0.850. Looking at the critical value, being careful because this time we've got a 10% significance level, gives us a critical value of 0.5476. So this time we end up rejecting H0. At 10% significance level, there is sufficient evidence to suggest a negative correlation between the ranks, remember, of the population density and the ranks of the distance from the town centre of the suburbs. So as we had with PMCC, we also have two-tail tests. And again, these will talk about correlation and association, and they won't specify a direction. Here, our RS for H0 is going to be RS equals 0, and our H1 is going to be RS is not equal to 0. Again, critical value table, but this time we're going to look up our percentages from the bottom row. So you can see there, two-tail, whatever our significance level is, we'll be choosing off that bottom row. So for the example, we have Miss Huggett wants to know if there is an association between how well her pupils perform on an arithmetic test and how well they perform on an English test. So straight away from this, we know that it's two-tailed. The results are in the table below, and we're trying to use a 10% significance level to test if there is an association between the two. So our H0 is going to be RS equals 0. Our H1 is going to be RS is not equal to 0. And then we need to rank our data from smallest to biggest on both sides. So that means that the 0 is going to get the rank 1, 8 gets the rank 2, 14, 3, 18, 4, 23, 5, 27, 6, 33, 7 and 45, 8. On this side, our smallest one is the 1, then 9, then 13, then 18, then 19, then 20, then 31 and then 33. Just as we did before, delete anything that you already have in your calculator. Typing in just the ranks, remember, so 8, 7, 6, 5, 4, 3, 2, 1, 7, 8, 4, 6, 5, 2, 3, 1. Quickly double check that you enter them correctly. And that gives us an RS value of 0.881. Oops. Sorry, my S is a bit big there. Remember that that's your test statistic. The critical value this time, we have 8 sets of data, 10% two-tail, so two-tail, 10%, 8 pieces of data gives us 0.6429. And again, as our test statistic is bigger than the critical value, we reject H0 at a 10%. Whoops. Significance level. There is sufficient evidence to suggest an association between the rank of arithmetic grade mark and rank of English score. Again, making sure that you use the word rank in your conclusion. I'd now like you to pause the video and give the Now You Try a go. Being careful because again, this time we have grades. Remember to give the smallest grade, A, B, C, D, E, F, G, will be the smallest grade. And make sure that you rank both of the tests separately. So hopefully you have paused the video and given the no you try go. As you can see, RS equals 0 for our H0 as always with Spearman's rank. This time our correlation, so not equal to for the H1. Then ranking the data, as I said before, G is the smallest, so both the G's have got 1s in the separate sense of data and so on. Putting that into our calculator gives us an RS of minus 0.25, which is our test statistic. Because we want to make that positive, the size of our test statistic is 0.25. Critical value, be careful, because this time we're using a 2% significance level. So two tail, 2%, then go down to 7. That gives us 0.8571. So as the size of the test statistic is smaller than the critical value, we accept H0 at 2% significance level. There is insufficient evidence to suggest a correlation between the rank of the first and second test. Thank you very much for listening.